Gotta be honest, I'm not 100% sure that this guy's name is pronounced Le Chatelier. But that's how I've heard it pronounced before, and it sounds pretty cool, and so that's what we're going to call it. We're talking about Le Chatelier's principle in this video here. So Le Chatelier's principle seeks to answer the question, what happens when you change something in a system that is already at equilibrium? So you have a reaction, it's sitting there, it's happy, you have reactions going forward, reactions going back, and then some punk comes along and is like, I'm gonna mess with it. The punk being you, as a chemist, and you mess with the reaction. Maybe you add some reactants, or maybe you heat it up, or maybe you pressurize it, or you do something to it. You mess with the equilibrium. Le Chatelier's principle helps us figure out what the reaction is going to do in response to being messed with. So what Le Chatelier's principle says is that if a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. If that sounded slightly like Greek, that's okay. Essentially what that is saying is if you mess with the equilibrium messes back. And I mean that pretty much literally. Whatever you do, the equilibrium pushes back. So if, for example, we have an initial equilibrium like this. We have a relatively small amount of two reactants and a decently large amount of a product. If we mess with the equilibrium by adding in some extra reactant, so we just plop some more in there, what the equilibrium is going to do is it's going to say, hey, I was happy the way I was. I want to get back to where I was. And so the reaction is going to shift in order to try to undo what you did, to get back to where it was before. Now it will not. It will never get back to where it was before, unless you do something else to make that happen. But just the reaction by itself will never get there, but it will shift in that direction. Specifically, since you added in extra reactant, it is going to shift to consume some of it, to eat up some of the stuff that you added in. And so what it's going to do is it shifts to the right to use up some of this reactant, but then as a result, not only does it use up this reactant, it also uses up some of this one, and it produces some extra product. But it doesn't really care about those other things. It is just trying to, it's reacting to the disturbance that you put on it. So the same type of thing would happen if instead of adding some reactant, if we took product out. If we removed product, if we took a chunk of this out, just pulled it out of the mixture, the reaction would shift to the right. You took product away, the equilibrium says, hey, where'd the product go? I had the amount I wanted. And so it will try to make more to undo what you did, to try to get back to the concentration that it was at before. It's always going to respond to counteract what you did, to do the opposite of what you did, which can be really, really handy, as we'll talk about in a little bit. So that's what happens when you change the concentration of something. You can also mess with an equilibrium by changing the pressure. So if you have a gas, at least one gas, involved in a reaction, and you pressurize the container, which is to say you decrease the volume of the container. You squash it down so that the molecules have less space to move around in. What that's going to do is it's going to increase the pressure of all of the gas particles inside. Their partial pressures will increase, and so the equilibrium is going to shift to try to reduce that pressure. So it's going to shift towards whichever side of the reaction has less gas. Now, if both sides of the reaction have the same amount of gas, well, then nothing's going to happen. The equilibrium can't do anything at that point. But if you have a reaction and one side of the reaction has one gas molecule and the other side of the reaction has 3, if you increase the pressure on that container, the reaction is going to shift towards the side that only has the one gas. It's going to shift towards the lowering of that pressure. Now, I'm going to specify and strain here that this is only going to happen if you decrease the volume of the container. If you just add in some other gas that increases the pressure on the container itself, but it does not increase the partial pressure of the reactants or the products, well, then that's not going to have an effect at all. This is only seen if the pressure of the individual molecules, the actual products and reactants, if their partial pressures increase, then you'll see the change. Just adding in some inert molecule does nothing. It doesn't have an effect. Lastly here, if you change the temperature on an equilibrium, the response from the equilibrium will depend on if the reaction is endothermic or exothermic. And you can determine what's going to happen by thinking about heat as either a product or a reactant. So for an exothermic reaction, heat is essentially a product. Heat is produced by the reaction. It is given off by the reaction. And so because of that, it would be like up here thinking of concentrations, just adding in heat as an actual product. And so if you put in extra heat, which is to say if you heat it up, if you increase the temperature, that is the same as adding in an extra product. So that would shift the reaction to the left, because it's trying to undo what you did. If heat is a product and you put in more of that product, the reaction is going to shift to essentially consume that product, to move it out of there, to get it out. And the opposite is true if you decrease the temperature. Endothermic reactions, this is when heat is like a reactant. And so it is just going to be the exact opposite of exothermic. And so when we're dealing with temperature, again, the easiest way to think of it is just to remember in exothermic reactions, heat is a product. In endothermic reactions, heat is a reactant. You actually need to suck heat from the surroundings in order for the reaction to take place. And so if you can think of it that way, it should become clear which direction the reaction will shift if you either add in more heat by raising the temperature or lower the heat by decreasing the temperature. And so when you have these disturbances, like you can see here, so this system is at equilibrium, the concentration isn't changing, and then somebody comes along and just plops in a whole bunch extra of this molecule. The reaction then shifts to consume that extra stuff that you put in, and eventually it reaches equilibrium again. Now notice it's not the same equilibrium concentrations that you had before, and that's fine. It doesn't have to be. As long as the ratio is the same, it's fine, and the ratio will be the same. But the actual equilibrium concentrations themselves will be different than it was before you messed with it. So really briefly here, the Chatelier's principle is used quite a bit, especially in manufacturing. One of the earliest and most important uses of the Chatelier's principle and what's called the, I'm going to butcher it, this is a German name. I think it's like Haber or Haber or something like that. It's not Haber, but it looks like it should be Haber. But anyway, this process of producing ammonia uses the Chatelier's principle because you heat up the gas and the gas reacts to form ammonia, and then when you cool it down over here, when you pull the ammonia out, because the ammonia liquefies at a much higher temperature than all the rest, when you pull that out, you're removing all the product from the equilibrium that's been built up. And so it pushes the reaction to make even more ammonia. And so this was one of the first situations where Le Chatelier's principle was used to essentially push a reaction to make more product by removing the product. And that's what they were doing here. And this actually revolutionized agriculture, because the main use for ammonia is in making fertilizers. And there was a real problem in Europe at the time of just depleting the land, where all the nutrients in the ground were just used up, because there was only so much horse crap to use as fertilizer. Like there's a limit to how much naturally occurring stuff you can use as fertilizer. And so they needed something that they could make, some kind of synthetic fertilizer. And there wasn't an efficient way of doing it until this. So this was actually one of the most important chemical process discoveries really ever, even though you don't really ever hear about it. So that is one of the first and most important uses of Le Chatelier's principle. So here again you can see shifting of the equilibrium based on temperature. So these two vials are exactly the same vials, just one of them is really cold and the other one is hot. And so it shifts the equilibrium one way or the other, depending on the heat. Real quick here, let's look at a practice problem where we have a reaction that we've seen earlier, actually, I believe, in this chapter. And it asks us, what is the effect of adding additional CO2 to the mixture? And what is the effect of adding additional calcium carbonate to the mixture? So think about that for just a minute. Pause the video, see if you can come up with an answer, and then come back. Okay. So, if we think about this first part here, what's the effect of adding additional CO2? The CO2 is a product, and so if we add in more product, what that's going to do is it's going to shift our reaction to the left. And this is not just true in terms of that it's a product, it's actually also true in terms of what we discussed in terms of the changing of partial pressures of things that are involved. If we add in more CO2, the partial pressure of CO2 is going to be greater, and so thinking of it in that terms as well would push the reaction to the left. So that would result in a leftward movement in the equilibrium. The second question, what is the effect of adding calcium carbonate? This is a little bit of a trick question, actually, because at first blush it seems, oh, we added in extra reactants, that'll push the reaction to the right. However, calcium carbonate is a solid. So a solid is not going to have an effect on the equilibrium. Again, it has to be there. You have to have some calcium carbonate, but the amount of calcium carbonate is completely irrelevant. As long as there is some, you will have this equilibrium. And so there will actually be no change for this one. Let's look at another quick example here. So we have a reaction, and it tells us what is the effect of decreasing the volume of the reaction mixture, increasing the volume of the reaction mixture, and adding an inert gas. So if we decrease the volume of the entire mixture, what that's going to do is it's going to increase the partial pressure of everything inside of the reaction vessel. So what that's going to do is it's going to shift the reaction towards the side with less gas. Because again, if we increase the pressure, the equilibrium is going to respond by trying to decrease the pressure. It's going to try and undo what you did. And so if you increase the pressure, it's going to try to decrease it by shifting, in this case, to the left. Because, excuse me, because there's no gases on the left side of the reaction, and there are 3 on the right. So the exact opposite is going to be true for the next one here. So if we increase the volume, that means we decrease the pressure, and so the reaction would shift towards making more gases. The last one is again a little bit of a trick question, because if you add an inert gas, yes, the overall pressure in the container will increase, but the individual partial pressures will not. And so this would have no change. All right. Last little thing here, catalysis. If you remember from kinetics, catalysts sped the reaction up, so that must mean that the catalyst is going to move the equilibrium constant to be more product favored, right? No. The equilibrium constant is actually not affected by catalysts at all. All it does is it gets you to equilibrium faster. So if you have a catalyzed reaction versus an uncatalyzed reaction, the hump here, the height that you have to get up to, is less in the catalyzed reaction, but the starting point and the ending point are exactly the same. And that is all the equilibrium constant is looking at, is where did you start, where did you end? Products and reactants. And so if the products and reactants are the same, it doesn't care how difficult it was to get from one side to the other. Now you'll get there faster. Like I said, the catalyzed reaction reaches equilibrium a lot sooner than the uncatalyzed one does, but it still reaches the same equilibrium. It has no effect on the equilibrium overall. All right, we made it to the end of this chapter. If you have any questions about this, feel free to email or ask me the next time I see you in lab. But for now, good luck on the homework, and I will see you in Chapter 14.